Welcome to NE204 Lab 6. The goal of this lab is to study the Hodgkin-Huxley neuron, the HH model, arguably the most important model in computational neuroscience. So what we'll do today in lab is we'll simulate the full model, the Hodgkin-Huxley model, to understand how the voltage and the different gating variables evolve in time. In this lab, as in all of our other labs, you'll see there are many comments. Those comments are hopefully helpful to you to understand what's going on. And I always encourage you to make comments in your own code. It's a good habit to have, and it's useful when you share your code with other people or when you come back and look at your own code sometime in the future. Okay, so let's start in part one with a simulation of the Hodgkin-Huxley model. In class, we wrote down equations for the Hodgkin-Huxley model, and we found a very complicated system of four coupled differential equations. To study how this system behaves, you might think, well, maybe I can do some mathematical analysis and find a solution. Turns out it's too hard. You can't do that for this system. It's just too complicated. So what we're going to do here is compute numerical solutions to the Hodgkin-Huxley model and see how the dynamics evolve in time. To do that, we're going to use some MATLAB code, which you can download from Blackboard. Now please download this function, hh0.m. You might wonder why I include the zero. This is the first type of model, or the zeroth order Hodgkin-Huxley model. You can do some extensions of it, make it more complicated, or try to simplify it, and I might use other numbers for that. So I'm going to call this hh0. This is the fundamental, the most basic Hodgkin-Huxley model. And look, what we'll do now is let's examine this code. Let's examine this code and see how it behaves. So let's open up this function. Let's open up hh0. I've downloaded it here. I can see it in my browser, in my editor. So I'll open up this function now. And to start making sense of this function, let's look at the inputs and outputs. Now we can see in this first function line, there are two inputs to our function, I0 and T0. I0 is the amount of input current that we get to specify, and T0 is the total time to simulate, where that time is in milliseconds. How do I know that? Well, luckily we have this comment at the top of the code that tells us T0, again, the total time to simulate, in what units in milliseconds. So we can read that here, and we see there are two inputs. If we look at the outputs of the function, we see that there are 5 outputs. Here they are, and maybe we can guess what these outputs correspond to based on our knowledge of the equations in the Hodgkin-Huxley model. V, as you might guess, is the voltage of the neuron. M is the activation variable for the sodium current. H is the inactivation variable for the sodium current. N is the activation variable for the potassium current. And then T is a time axis of the simulation. And that's useful for plotting. It's not something necessary, but we'll see it's useful as we go along. Okay, so those are the inputs and outputs of the function. It's always good to understand that when looking at a new function. But now let's dig into the function body and see how it works. And we'll do that here. So let's look at how this function behaves. Now what we see at the beginning of the function in line 18 through 22 are a bunch of variable definitions. We might be able to guess this dt is the step size, t is the total duration of our recording, or the total number of steps it will take. Notice it's our total time divided by our time steps, so that should give the total number of steps to take in the simulation. And then we define important parameters in our Hodgkin-Huxley equations. We have the maximal conductances of sodium, of potassium, and of the leak current. And we also have the reversal potentials for sodium, potassium, and our leak or resting current. So we can see all of those here. All of these parameters are defined in lines 18 through 22. So those are all fixed quantities, fixed numbers. And we should be able to look at these different values for GNA, GK, these maximal conductances, and also look at these reversible potentials that we see here. And hopefully they should match what we have in our notes and our expressions for the equations. Good. So what's happening now in lines 24 through 28? Well, what we observe here is definitions of some variables. And notice we have the variables t, v, m, h, n. Those correspond to our 5 outputs for our function. So notice what we have here. Let's look at t. This is going to define our time axis. What we'll do is we'll go from 1 to big T in steps of 1. So that's the total number of steps we'll take in our simulation. And then we'll multiply that by dt so that we make each step of size dt. So we'll take whatever we specify for dt. In this case, remember, units of time are in milliseconds. So we're going to take steps of 0.01 milliseconds, and we're going to take a total of big T of those steps. The variables v, m, h, and n, here we define to be all zeros. What are the size of these variables? They have, we specify 2 inputs to our function zeros. We first specify big T, which again is the total number of steps we'll take in our simulation, comma 1. So this is going to make a long list of zeros. It's going to have T rows. We're going to have a bunch of rows in one column. So you can think of this as one long vector. And we're going to do that for V, M, H, and N. One reason to do this is we'd like to specify the dimensions of our output. So here we know the dimensions of our output are going to have t rows and 1 column. We don't have to do this in our simulation, but it's often very useful to do this because we're kind of pre-allocating this space, the length of the variable, and then MATLAB is just going to put numbers in there. So MATLAB can take the results at different time steps and stick them into our variable v, which already exists. If you don't do this, it might slow down your code, which is one reason to do this, right? We want our code to be as fast as possible. Another reason to do this is we specify the dimensions of our variables. So we fix the dimensions of v, m, h, and n. And that can be useful. It serves as a double check. We can already start thinking about the size of our outputs, and that may help us in our coding procedure overall. Pre-allocating the space, it's faster, and it forces us to think about the size of our variables. Okay, and then what? Let's specify initial values for our 4 variables in the Hodgkin-Huxley equation. So we're going to set our initial value of v to minus 70 millivolts. Notice we're going to index v here at index 1. So we're going to take the first element of our vector v and set it to minus 70. That's going to be the first value. And we'll do the same thing for m, h, and n. We set these initial values. And I've chosen these in a particular way. You might try other initial values and see how the system behaves. But let's stick with these for now. Okay, then what happens? We're going to get into the heart of our function. So we're going to generate a for loop, and this for loop is going to move us forward in time. So we're going to take steps of 1. So we're going to take this variable I. It's going to go from 1 to big T minus 1. We'll see why T minus 1 in a second. And we're going to move forward in steps of 1. So we're going to try to index our variables. You'll see we're going to try to index our variables v, m, h, and n, moving forward sequentially in time. So how do we update our equations? We use a prescription that we've used in our other model systems. We'd like to know what is the value of v one step in the future. Well, to find it, we're going to take the value of v now. We're going to add to it our little step size, dt, and then take the right-hand side of our differential equation for the Hodgkin-Huxley model, in this case for the v variable. And if you look at this highlighted code, I'll try to highlight it here. So if you look at this highlighted code, we should be able to decipher this highlighted code. And if you look at this code and compare it with your notes, you might see here we have the code for the sodium current. We could see the maximal conductance, GNA. We could see the activation variable, M cubed. We could see the inactivation variable, H, and we're multiplying all of that by the reversal potential and the voltage. So here, this first highlighted term, and I'll select here, is the sodium current to our model. Notice we're using the value of our variable M at step I, and H at step I, and V at step I. So we're taking the current values of these 2 gates, M and H, and our voltage V, and we're using that to update, to step forward in V one step, one index in our vector. Okay, so this first term that I'll highlight here, we've said that this first term corresponds to the sodium current. What about this second term? Well, if we look at this second term, we might recognize the potassium current. We see we have the maximal conductance, GK. We have this gating variable N. We're going to raise it to the 4th power. And then we have the reversal potential minus the voltage, shown here. Good, so this second term corresponds to our potassium current. And again, notice we're using the current values of our potassium activation variable and our voltage V. And we're using that to update, step forward one step in time to the future voltage of V. Finally, we have our leak current. You see that here. We have our maximal conductance for our leak current, and we multiply it by the reversal potential minus the voltage. In our last term, we have this injected current. So that's some current we specify that we can use to drive our model system. Acts to change the voltage. So again, the first line of this for loop, this is implementing the machinery of the Hodgkin-Huxley equations, in this case for the voltage variable. So what's happening in the second line of this for loop? Well, what we'd like to do is figure out the future value of our variable M, the activation variable for our sodium current. How do we find this future value of M at index I plus 1? Well, we look at the value of M right now at index I, and we add to that dt times our differential equation. And let's look at this differential equation. So we can look at this differential equation. And what do we have? Well, we have this alpha M, and this looks like a function, right? Alpha M that's taking the input Vi, and we're multiplying that by 1 minus Mi. So the current value of V is applied to this function alpha M, and then the current value of our gate Mi. And then we have from that minus beta V times Mi, where this beta MV, is also a function. Beta M, we send it an input Vi, and we're multiplying it by the current value of M, sodium activation gate, at index I. Okay, so what do we notice about this expression? We want to go forward one step in M. We use the current values of M and the current values of V. You might remember from our notes we had different ways of expressing the differential equation for M. We could use the equilibrium value and the time constant, or we could use this forward rate function and a backwards rate function, and that's what we're using here. So if you look back at your notes, we should be able to see these equations for the forward rate function and the backward rate function. And another reasonable question is, what is this function alpha m? Well, this function is defined within this file. So notice if we scroll down to line 45, we have another function call, right? Function. It's going to return one output am, and it's going to take one input v. So we have our new function alpha m, takes one input v, and returns this am. And we have this expression, am is equal to all this stuff. Where does all of this stuff come from that we've highlighted here? Well, these are the expressions Hodgkin and Huxley solved for in their research. And those are the expressions we've implemented here. We do the same thing for beta m, backwards rate function. We have another function that we call for that. It takes one input, the voltage. Right? We're going to take the voltage Vi. We're going to send it to our function beta m, where that function beta m is defined right here in lines 49 through 51. That function takes the voltage, it does some manipulation to it. This complicated expression has an exponent, it's dividing by stuff, and returns this variable beta m. Good. Where does this expression come from? Right, this expression comes from the equations that Hodgkin and Huxley solved for in their original work. And we're just implementing it here. So again, we'd like to step forward one step in time in our sodium activation variable. We do that by using the current value of the sodium activation variable and then the equations that Hodgkin and Huxley found. So this equation Hodgkin and Huxley found where you have to implement alpha m and beta m as new functions, which we do here. This exact same prescription works for the updates of our sodium inactivation variable h. We want to know its value one step in the future. We take its value now, and then we add to it dt times the differential equation for h, our sodium inactivation variable. And the same is true for our potassium activation variable. This variable n, we want to know what is its value one step in the future. We take its value now, plus dt times our differential equation. Right? And you might notice that the forms of the differential equations for m and for h and for n, these three differential equations, they're very similar. Right? We have 1 minus m, 1 minus h, 1 minus n. All of them are multiplied by these alpha functions, where we have alpha m, alpha h, and alpha n. Those alpha functions are defined below. So if I scroll down, between lines 45 and 67, we have all of these different alpha functions. We have alpha n, alpha h, and alpha m, where these expressions are defined, or were found by Hodgkin and Huxley. They fit the data, they got these expressions, and those are the expressions we'll use here. Good, so that's the full Hodgkin-Huxley simulation. Again, let's think about what happens. We give it two inputs, the injected current and the total time of simulation. We define a bunch of parameters. Some of them we need for our steps, how many steps we're going to take and what is our step size. And we have other variables that we define related to the Hodgkin-Huxley equations themselves, right? The maximal conductances and the reversal potentials. We allocate some variables, v, m, h, and n. We fill them all with zeros, and then we're going to update these zeros and fill them in, right? Let's fill in the first zero at the first index for v, m, h, and n. We do that here. That's our initial condition. And then we're going to step forward in time. We're going to go to t minus 1 steps in the future. Why t minus 1? Because we're eventually going to add 1 to it, and we don't want to fall over the edge, right? We don't want to go to index t plus 1 because our variables are only defined up to index t. So we have to be careful to include this t minus 1. We're going to step forward into the future to find the value in the future. Let's say v, we figure out the value now, and then we add to it dt times what Hodgkin and Huxley found in their differential equations. And we're going to do that for v, m, h, and n. In order to do that, we need to define some auxiliary functions. Here they are, our forward and backward rate functions for our three variables, m, h, and n. We define all of those here with these complicated expressions, again, that Hodgkin and Huxley found through their experiments. So that's the function hh0. Let's now go back to our lab and try simulating that function. So we've covered all of this material, right? We've examined this code. We saw that there are two inputs to this function, 5 outputs. The first 4 are the variables of the Hodgkin-Huxley model, and then the last one is a time axis that's useful to plot. Let's now move into part 2 of the lab, where we'll actually simulate this model. Okay, now that we've looked at the equations, we've seen our model hh0.m, we have a sense for hopefully it works, or at least it's consistent with the equations that we developed in the lecture. Let's try to use it. So let's simulate this model and see how it behaves. And to start, let's fix our two inputs to the model. We're going to start by fixing I0 is equal to 0, so that's our input current. Let's start by setting it equal to 0. And let's simulate this model just for 100 milliseconds. So I'll set our second input t0 equal to 0. And with that, with those two quantities defined, we're now ready to simulate our function, our Hodgkin-Huxley model. So let's do it. Let's evaluate this function. I'll copy line 58, and what we're going to do here is we're going to simulate our model, hh0, so we're going to call this function. We have our input current I0, our total time of simulation 100 milliseconds t0, and we're going to return these 5 outputs. So if I hit enter, okay, it doesn't work. Right? This undefined function or variable, why wouldn't it work in this case? Why is this thing not working? Well, I'm probably in the wrong directory. So I need to navigate to wherever I downloaded this function. I guess I didn't download it to Documents, MATLAB, so I have to look, where did I download it? Well, I probably downloaded it into week 6, right? Lab week 6. So I navigate to that directory. Hopefully my function hh0 is there, so I'll call that function again. I'll copy this function here, paste it back in, and evaluate it. Okay, and it doesn't crash, so that's good. We didn't get that error message. I've now navigated MATLAB, the working directory, to the right place, wherever I downloaded this function. How do I know that it's worked? Well, if I look at my workspace, I now see that there are some new variables there. We have this variable h, m, n, t, and v. Notice that h, m, n, and v there have many rows, right? 10,000 rows in this case. That corresponds to our 100 milliseconds of simulation, where we're taking tiny steps, less than a millisecond each time. So we see that we have these 4 variables. And what we'd like to do now is ask some questions about these variables. So we have a couple of in-lab questions here. If I scroll down a bit, we can look at some of these questions. For example, what are the dynamics of the voltage variable, right, this variable V, resulting from this simulation? Remember, our injected current is 0. Well, how can we answer that question? If I type V at the command line, and again, a bunch of numbers, I'll do that again. I hit V, enter. We have a long list of numbers. How many numbers? Well, we have 10,000 numbers in this case. And as I scroll up through this list of numbers, right, not much is changing. It looks like it's stuck at some value. So printing out numbers is fine. That's one way to look at it. An easier way, or maybe a more informative way to look at this result, is let's plot the voltage versus time. So remember, our function hh0 also returns a time axis. Let's use it here, and let's plot t comma v. T is on our horizontal axis and v on our vertical axis. So this is the plot I get. And just to be clear, let's label the axes. So I'll label the horizontal axis. Let's X label. Let's set that equal to time. Remember, it's in milliseconds. And we'll set our vertical axis. Thank you. Yeah, I typed it in wrong. MATLAB's saying, did you? All right, this XLABLE is wrong. MATLAB's trying to suggest the right thing here. It gets it. Good. What about Y label? Let's set that to be the voltage in millivolts. Okay. So now we have our plot here. This is our simulation. We're looking at one variable V versus time in milliseconds. And what do we see? Well, we start at some initial value. If you look back at the code, we started a value of minus 70 millivolts. What happens? Well, we see a rapid increase in the voltage. We then have a couple wiggles here, and eventually it settles down. Where does it settle down? Well, at a value just above minus 65 millivolts, so somewhere in here. So what we find in this case, what we find in our simulation in this case, is that the voltage wiggles a little bit, but after about 50 milliseconds, it settles down at a fixed value. So that's our conclusion in this case for the variable V. What about the gating variables, right? What happens to the dynamics of the gating variables? Let's plot one of them here, and then you can consider what happens with the rest. So let's plot one of our gating variables. Let's plot t comma m. So we'll look at the activation variable for our sodium current. So we'll plot that here. I now have this function. Right, here's a plot. And let's label the axes. We'll again use X label. Remember, this is the time in milliseconds. While our Y label is our M gate. We'll just use that here. Okay, good. So here's our plot of our variable M versus time. What do we notice? Well, again, we have a rapid change in M early in the simulation, maybe less than 10 milliseconds. It looks like a rapid decrease and then an increase, then some wiggles, and then it settles down. So then the value of M settles down, and it settles down at some value. It looks like it's between 0.05 and 0.055, right? Somewhere in this range. And so if we had to describe qualitatively what happens, we have some initial transients, some wiggles in our value of M. It starts some value, wiggles around, eventually settles down after about 50 milliseconds to what looks like a fixed value. It looks like it's no longer wiggling. And you might wonder, does the same thing happen for our other gates, our H gate and our N gate? So I encourage you to investigate that, make plots of those and see what happens. And if you do that, what you'll find is that they all have qualitatively similar behavior. There's some wiggles at the beginning, maybe from 0 to 50 milliseconds, and then after that, the dynamics settle down. So we can ask a question, what are the final values? Right? What are the final values of all 4 variables after the 100 milliseconds of simulation? So how do we answer that question? Well, we can look at V and we want to know what is the last value of V. Well, we know V has 10,000 things in it, so we can look at the value of V at that index. Or another way to do that, we can call V end. So that's asking MATLAB, please find the value of V at the last index, the ending index. We get the same thing. And if we look back at our plots of V versus T, we should see that V settles down at approximately this value. And if you look back, you'll see that that is the case. If you plot, let's do it here. If we plot T comma V, so now I have this plot here. If we look, where does V settle down? It looks like it's just above minus 65. And in fact, we see it's at minus 64.9069. Good. And you could do the same thing to find the final values of our other gating variables. So what is M at the end? Right? What is the last value of M? And we get a value of 0.0535. If we plot T comma M, we see that that looks approximately right. We said it was some value where M settles down after about 50 milliseconds. It's somewhere between 0.05 and 0.055. In fact, it's 0.0535. And you could do the same thing for H and for N. You could find the final values. Where does it settle down at the end of the simulation? And the conclusion in this case, what we find in this case, is that this value of input, when I0 is equal to 0, so we can think of this as not injecting any charge to our model neuron, the model dynamics approach a fixed point. What does that mean, a fixed point? Well, that's some point where the dynamics become fixed. They're no longer changing. And that's visually clear when we make plots of, let's say, the gating variable, M in this case. We see that there are some initial wiggles, and then the dynamics settle down. So that's what we mean by a fixed point. They become fixed. If we look at the end of this simulation, near, let's say, 70 or 80 or 90 milliseconds, M is no longer changing. It's fixed. It's no longer changing in time. It's fixed at a value, in this case, of 0.0535. And you'll find that's true for every variable in this system. So by using the simulation, we can identify the dynamics of this system, a fixed point for the specific injected current I0 equals 0. We'll then, in the next section, inject more current to this model and see how it behaves. If we can get something maybe more dynamically interesting than a fixed point. In part 2 of the lab, we simulated the Hodgkin-Huxley model with low injected current. We set I0 equals 0. Now, in part 3 of the lab, let's increase this injected current and see if we can get the Hodgkin-Huxley model to generate action potentials or spikes. So let's try that. Let's set I0 equals 10. So now we've increased it from 0 to 10, and we'll simulate our Hodgkin-Huxley model using the same call to the function. We'll give it our 2 inputs, I0 and T0. Remember, we're going to set T0 equals to 100 milliseconds. And let's simulate this model with the 2 inputs, I0 and T0, and have it return our 4 outputs. And now we can ask a question. What happens to the dynamics of our voltage trace? Probably the easiest way to see what happens is let's plot the voltage, and we'll plot it as a function of time. So let's plot those 2 quantities. And when I execute that command, I get the following plot. It's always useful to label the axes, so let's set the x label equal to time in milliseconds, and the y label equal to voltage in millivolts. Good, so now we've labeled the axes, and let's look carefully at this plot. So what we find now, looking at the voltage on the vertical axis, the time on the horizontal axis, is that we have a series of rapid increases and decreases in the voltage. These correspond to the action potentials or spikes in the model. Notice the action potentials start at a voltage around maybe minus 70 millivolts and go all the way up to 40 millivolts. And this increase in voltage and subsequent decrease in voltage occurs very rapidly on the time scale of a few milliseconds. We find here that repeated spiking occurs at this level of injected current. And what we'd like to do now is focus on one spike in this plot. Let's focus on one spike and see if we can understand what happens during this spike to the gating variables. So to do that, we're going to generate two separate plots on the same window. We'll do that by using the subplot command. So here's the subplot command. We're going to give it 3 inputs. This specifies the number of rows as the first input, the columns in our subsequent plot, and then we're going to index which subplot we'd like to investigate. We're going to start with the first one. If you're interested in how this command works, you can check it out in MATLAB Help, or you can probably get a sense for how it works in the rest of this lab. Okay, so let's call this subplot command. So we're going to divide up our figure window. If we look at our figure window, we've created our first subplot. We haven't put anything in it yet, but MATLAB has at least allocated the space in our plot. We see it's in the upper half of our plot. Now, let's plot the voltage, and let's choose a particular time interval so that we can focus on a single spike, or action potential. And we'll do that here. So this is lines 103 to 105. Let's plot the voltage versus time, t comma v, and we'll make the plot black. So our voltage plot will be black. And then we're going to focus our x-axis on a particular range. So maybe I'll start by making the plot. So here's our plot. Again, notice we plotted the voltage in black. Why is it in black? Well, if we look at the third input to our function, it's a single quote k, single quote. That's telling MATLAB, please make this curve black. And we have this plot as shown here. Again, we're plotting voltage on the vertical axis, time on the horizontal axis. This is exactly the same as the first vaulted plot we looked at, except it's a different color, and we're using this upper subplot. And what we'd like to do is focus on a single action potential in this plot. We could choose any of the action potentials we see here, but let's focus on a particular one. Let's look at the action potential between 42 and 56 milliseconds. So to focus on that particular horizontal interval in time, let's set the x-lim, the x-limits for this plot to go from 42 to 56 millivolts. And let's label the vertical axis. So let's set the y label. We use V for voltage here, and remember the units are in millivolts. So if we look at the plot now, what do we see? Well, on the horizontal axis, we're only plotting times from 42 to 56 milliseconds. And notice the voltage still goes from about minus 100 to plus 50 millivolts. And we see the rapid increase and decrease in voltage. And we can see almost the time scale at which this increase and decrease occurs is on the time scale of a few milliseconds for the action potential to occur. Okay, so that's a plot of the voltage versus time. Now let's use the bottom half of our figure. We'll create another subplot to plot the different gating variables and see how those gating variables evolve during an action potential. So to do that, let's make a subplot. We're going to again use this subplot with 3 inputs. We're going to look at 2 rows. We only have 1 column, and now we want the second row, so the second space in our subplot. So I'll execute that here, and if we look at our plot, we see that we've now allocated the bottom half of this plot for us to put some things in it. Right now we haven't put anything in there, so MATLAB just makes this blank plot. And what we're going to do in this bottom subplot is we're going to plot the gating variables. And let's start with the gating variable m. So let's plot this gating variable m. We're going to plot it versus time. That's the first input. M is the second input. And let's make this plot red. So our gating variable m will be red. And then we want to be careful to investigate the same horizontal range. So the same time from 42 to 56 milliseconds. So I'll do that here. We'll evaluate this plot, and let's look and see what's changed. So if we look at our lower subplot, again, we're plotting only one gating variable, m. We see it ranges from 0 to 1, which is what we expect for a gating variable. And here we're plotting it from 42 to 56 milliseconds on the horizontal axis. And what do we observe? Well, at 42 milliseconds, it's near a value of maybe 0.1. It's mostly closed. Then as time evolves, there's a rapid increase in this gate. Right? M rapidly increases to 1, and then sometimes later rapidly decreases to 0. And then it has a slow, gradual increase back to some baseline value. So this is just one of the gating variables. Let's plot the other 2 gating variables and see how they evolve during this single action potential. To do that, first thing we need to do is freeze our graphics window. So in line 122, we're going to type hold on. That's going to freeze the graphics in our lower plot. And now we're going to tell MATLAB to plot our other 2 variables, h and n, as functions of time. Again, by freezing the graphics window, we'll make sure we don't erase the plot of m that we already have there. And let's plot our 2 other gating variables. So let's plot t, comma h. So our sodium inactivation gate, let's make that blue. And we'll also plot our last gating variable, T, comma, N, our potassium activation variable. And let's make that plot green. And finally, we don't have to turn hold off, but it's usually the polite thing to do, so I'll turn hold off. Okay, so here we have a plot. Now we have three curves that correspond to our different gating variables. Let's label our axes. That's always a useful thing to do. So let's set the X label. We're going to remember that that is time in milliseconds. We're only investigating a small range of milliseconds. Notice I put square brackets around this expression. You don't have to do that. I'm going to do it here. I hit execute. I actually missed that last one of the square brackets. MATLAB reminded me I should probably include it, so that's good. And now it's also useful to add a legend to this figure. Why might we want to add a legend? Well, if we look at our plots, we have these three different curves. And maybe you can remember what the red curve represents and the green curve and the blue curve. But I think it's most helpful to have a legend so we can look at our legend and decide what color corresponds to which gating variable. So let's call a legend. We're going to put a legend in our plot. Remember, the first curve we plotted was M, the second curve was H, and the last curve was N. Okay, so we evaluate the legend. MATLAB is smart enough to know what colors those correspond to. And now we can ask some interesting questions. And probably the most important question that we can ask is, how do these gates evolve during a single action potential or spike? So what I would recommend right now is to pause this video, think about this question. How do these gates evolve during a spike? And see if you can make sense of how these gates evolve and how they're useful for establishing this action potential or spike. Then, after you've thought about this, come back to this video and I'll give you some ideas about how these different gates evolve and why it makes sense. Okay, so hopefully you've spent some time trying to understand why these gates evolve in the ways that they do, and in particular, how they relate to the voltage that we see in the top subplot. So let's see if we can make sense of what's happening here. So let's start by thinking about the upswing of the action potential. So what happens during the upswing of the action potential when we have this rapid increase in voltage? Well, notice what we observe. The M gate is rapidly changing from a value near 0.1. It rapidly increases to a value of 1. So this is telling us that our M gate is rapidly swinging open on a timescale of less than a millisecond. So we have this rapid swing open in our M gate that corresponds to the rapid voltage increase, this depolarization of the voltage from about minus 50 to plus 50 millivolts. Why does this make sense? Well, remember the M gate is gating our sodium ion. When this gate swings open, it allows positive sodium ions to rush into our cell. And if we have positive sodium ions moving down their concentration gradient and rushing into the cell, because our M gate is now open, how does that change the voltage? Well, we have positive ions rushing in, these sodium ions rushing in down their concentration gradient. That should rapidly increase the voltage. Positive ions moving in, the voltage rapidly increases. Okay, so that's the first step. That's the upswing of our action potential. The M gate rapidly swings open, sodium ions rapidly rush in. Then what happens? Well, as time evolves, now we have a couple of things changing. Let's first look at H. So let's look at this blue curve. So what happens? We've reached the peak of our action potential. Now what happens? Well, we see this H gate goes from a value of nearly 0.5 to a small value, maybe near 0.1. So what does this do? What is the effect of this H gate changing? Well, we see that the H gate goes from partially opened to mostly closed. It's from a value of 0.5 to a value closer to 0. So this H gate is swinging closed. And what is the impact of that? Well, when this H gate swings closed, it blocks the sodium ions from entering the cell. By blocking the sodium ions from entering the cell, we've removed this source of depolarization. When the M gate swings open, it allows sodium ions to rush in. Eventually, the H gate closes, and that prevents those sodium ions from rushing in. So that's one way in which we stop the depolarization of the cell. Something else happens as well. Let's look at our N gate. So we see that our N gate starts at a value of approximately 0.4, and then it increases, and it goes up to a value of maybe 0.8. So what happens as this N gate swings open, as it goes from a value of 0.4 to approximately 0.8? Well, as this gate swings open, remember it's gating the potassium ions. So if it's gating the potassium ions, you might remember that the concentration of potassium is higher inside of the cell than outside of the cell. So if that's the case, and this N gate swings open, what happens to potassium ions? They move down their concentration gradient and out of our neuron. So we have these positive potassium ions. They can now leave our neuron because the potassium gate is open. And if we have positive ions leaving our neuron, what does that do? Well, that helps to hyperpolarize the voltage. So the voltage starts to decrease as these potassium ions are sent away. They can now move out of their N gate down their concentration gradient. And so these two effects, our sodium gate being blocked by the H gating variable, it's closing, and our potassium gate opening up, these two effects act to allow hyperpolarize the neuron. So we get this decrease in the voltage. If we wait long enough, maybe 5 or 10 milliseconds after the action potential, we see that the variables return to their steady state values. In this case, maybe 8 milliseconds, right? There's this overswing, this hyperpolarization. Why is there hyperpolarization? Well, this H gate stays open a little longer, has a bit slower dynamics, and the N gate stays open a little longer, right? We could see it here. We have this green curve going up, and then it slowly tapers down back to its value of approximately 0.4. As this gate is open, it allows potassium ions to leave. That continues to hyperpolarize the cell, so it goes down below its resting potential. Also, our sodium gate is still closed, right? It's blocked by our H variable, and also our M variable is essentially 0. So there's no potassium or no sodium ions that are allowed to enter the neuron. So this is perhaps the most important model in computational neuroscience. If you can understand these two curves, the voltage trace and these three colored curves, and tell the story of how an action potential evolves and how these gates swing open and swing closed, you'll have a very deep understanding for how this model behaves. In part 3 of the lab, we explored how the three gates, M, H, and N, how they swung open and swung closed, how they evolved during an action potential. Now, what we'll do in this last section, part 4, is we'll combine these terms and visualize how the conductances evolve in time. In particular, how they evolve during a spike. To do so, we're going to use the same settings we used in part 3 and simulate the model focusing on a single action potential, or spike. So let's do that. Let's set I0 equals 10. So we're going to drive our cell with enough current to make it spike. We'll then simulate our neuron again. Maybe we don't have to do this. Maybe we have the variables already from part 3, but I'm going to do it again just to be safe. And let's generate a subplot. So we'll generate a subplot with 2 rows, 1 column, and we'll start with the first entry in this subplot. And in that subplot, so MATLAB here will make that blank subplot, we're going to plot the voltage versus time. So plot t comma v, and let's make that curve black. And if we look at the curve now, so what we're plotting here is voltage versus time. We see a bunch of action potentials are occurring because we're driving the cell with enough input. Let's focus on one of those action potentials between 42 and 56 milliseconds. To do that, let's set our x limb, and let's also label our y-axis to remind us that it's the voltage we're looking at, V. And so here is the isolation of a single action potential or spike as part of this simulation. You could pick other spikes to look at and see if they're different. They won't be. We'll get the same dynamics. So we're just going to pick one to investigate. Now, let's plot the conductances. Instead of plotting the gates and how they evolve in time, let's plot the conductances. And we're going to do that using the code in lines 61 to 63. And a question, so let's evaluate these three. Well, let's think about the first one. So we have this, we're going to define this new variable GNA. What is it equal to? Well, we're setting it equal here to 120 times m cubed times h. Where does this m come from? Well, this m is an output of our Hodgkin-Huxley model simulation, and this h is an output of our Hodgkin-Huxley model simulation. We're multiplying them together. Now, m and h are both vectors. If I look at my workspace, I could see m, it's a 10,000 by 1 vector, and h is a 10,000 by 1 vector. So we're going to multiply these vectors together. Because we're going to multiply them element by element, we need a dot star to multiply them together. And also notice we're going to raise m to the third power. We have an m cubed h term, and so we need to raise it to a dot hat 3 because we want to cube each term in that vector, each element of that vector. We'll do the same thing or something similar for our variable gk. We're going to take this number 36. Where does that come from? You might think about that. Times n to the fourth, where n, again, is the output or one output of our Hodgkin-Huxley simulation, and we're raising it to the fourth power. We're going to do that element by element, so we have this dot hat term. And finally, gl, that's our leak conductance. We're setting it to be a constant, 0.3. So where do these terms come from? Well, there's a hint here, right? We can wonder where do these terms come from. One hint is to examine the Hodgkin-Huxley equations. and see if you could find these terms. In particular, can you find this 120 times m cubed times h, and can you find this 36 times n to the fourth? Can you find those terms in the Hodgkin-Huxley equations? Maybe you look at the function hh0 that we have here, or maybe you look back at your notes. Okay, so now let's plot these conductances and see what we find. And we've already plotted in our upper subplot the voltage versus time. Let's plot in our lower subplot. Again, we're going to have 2 rows, 1 column. We're going to look at the second subplot. Let's plot in that second subplot the sodium conductance versus time. And let's make that curve magenta. So that's the third input, m. That function is not yet defined. Why is that? Oh, I forgot to execute lines 161 to 163. So I'll do that now. Let's try it again. Let's try to make this plot T versus the sodium conductance GNA. We'll make it magenta. I don't get anything crashing here. Let's look at our plot and make sure. We see we have a lot of funny things happening here, a lot of spikes in this GNA. It's a magenta, so it's this pink color. Notice the time goes from 0 to 100 here. Eventually, we're going to zoom in on a particular interval from 42 to 56 milliseconds, just selecting one spike. So we'll get to that. But first, let's freeze our graphics window in this lower subplot, and let's plot our potassium conductance and make it green. And let's plot our leak conductance. We'll do that here, and also make it black. Notice GL is just a number, 0.3. We want to plot it versus time, so what we're going to do is multiply that constant by a bunch of ones that have the same size as t. This is just a trick because when we plot a vector versus a vector, we want them to have the same number of elements. T is a vector. If we look at t, we see it has 10,000 things in it, so we want to take GL, which is a constant, and multiply it by 10,000 ones. With that, then we'll turn hold off, again, which is not necessary, but is polite. And let's set our xlim to focus on the single action potential or spike. Let's also label the axes. So we'll set the horizontal axis to be time. Again, that's in milliseconds. Our vertical axis, we're going to set to be micro MHOs, which is ohm backwards. Ohm is resistance. Here we're looking at conductances. Units aren't really important here. But if you're interested, you can have a look at that. And then let's label our 3 different conductances. We have GNA, GK, and GL. And now, let's look at our plot. And can we describe how the conductances evolve during an action potential? So here, we're not looking at the gates necessarily. We're looking at combinations of gates. And these combinations of gates determine how the different conductances open and close. So you might think about this plot. And can you understand, or can you make sense of how these different curves evolve, how these different conductances evolve, and does it make sense when you compare it to the voltage evolution? Think about that, spend a few minutes thinking about it, and then if you're interested, you can continue on with the rest of this lecture. But again, think about it first, see if you can come up with an answer, and then I'll give you some clues. Okay, so let's think about this magenta curve. We said that's the sodium conductance, GNA. And we see that the sodium conductance is very tiny, and it's near 0. And then the sodium conductance rapidly increases, and this corresponds to the upswing of the spike. So when the sodium conductance increases, it's like a bigger sodium hole in the membrane that allows more sodium ions to enter and depolarize our neurons, so the voltage goes way up. This conductance reaches a peak and then starts to decrease. As this decrease occurs, we're closing off this sodium conductance. We're making this channel smaller and smaller and smaller, so sodium ions are harder. It's harder to get sodium ions to enter the cell. Right, that channel is getting smaller and smaller and smaller. That hole's getting smaller and smaller and smaller. And at some point, that hole gets so small that the sodium ions can no longer enter. And so this prevents further depolarization, further entrance of these sodium ions to our neuron. So what else is happening at the same time? If we look at our potassium conductance, we see that sometime later, so we have this initial upswing of the sodium conductance that depolarizes the neuron. It's followed by an upswing of the potassium conductance. What happens when this potassium conductance goes up? We have a channel for potassium, or a hole. That hole gets bigger. And as that hole gets bigger, the potassium ions can now leave the interior of the neuron. They can leave the interior, go down their concentration gradient, and leave the cell. And as these positive ions leave the cell, they hyperpolarize the neuron. We have positive ions leaving that causes the voltage to go down. So as the sodium conductance is turning off, We're preventing positive ions from entering, positive sodium ions from entering. We're opening up this potassium conductance. And as this conductance opens up, we're allowing positive ions, the potassium ions, to leave the neuron. And that acts to hyperpolarize the voltage. And this occurs for some amount of time. We get this strong hyperpolarization of the neuron. It shoots below its baseline value and eventually recovers. There's also a leak conductance here. It's not changing in time. It's at some fixed small value. You can just barely see it as this black curve at the bottom of the figure. So hopefully, again, by looking at these two different conductances, you could think about how ions enter and leave the neuron, how they move down their concentration gradients from a high to low concentration, and how that causes changes in the voltage and can produce this rapid upswing and then slightly more gradual downswing of the voltage.